Thanks.
Uh, Hello. Uh, I wanted to talk about the p-Bergman theory, and I just want to give an overview of this. So I don't have any proofs. So it is just a bunch of results that I have. Uh, Hopefully, I'll talk through it. So, what is the space? What we are looking at the setup is we start with a bounded domain in Cn. And the Bergman space is defined as AP of omega, and it contains all the holomorphic functions in omega which are LP integrable. One of the nice things about these function is that it satisfies the something called as a Bergman inequality, which says so fix a point z in your domain omega, then f of modulus of f of z will be less than or equal to some constant times the p norm of f. So notice that this constant is independent of the function f. So this is for all function f in A. So if you now, yeah, so using the Bergman inequality, it can be easily seen that AP is a closed subspace of LP. So it is in fact a Banach space. When you are looking at p equals 2, A2 will become a Hilbert space with the usual inner product. Also, what the Bergman inequality says is that if you consider this functional Ez of f, if you define it to be f of z, so this is the evaluational functional at z. So evaluational functional will become a continuous linear functional. So now you know that by Rees representation theorem, you know that the dual of A2, any Hilbert space, is itself. So that is why there exists a function k depending on z, such that this evaluational functional is determined by this function k. So this function uh, k of w comma z, which is defined as kz, this function kz evaluated at w. So this is called the Bergman function, Bergman kernel function. So this is one of the like one of the important subjects in SEV. Uh, uh, when p equals to so and the properties of this Bergman kernel will inform us about the geometric properties of the domain. That is, if you look at how the kernel blows up, then that will tell you about the smoothness of the boundary and so on. So uh, now, why do we just not just restrict ourselves to p equals 2 and consider a general p case? That is because of one of the reason is it is nice to do and hard to do as well. But one other reason is if you restrict yourself to this kind what is called a hyperconvex domains. Let us not worry about what it means. But if you look at that, and if you look at p equals p between 1 and or 0 and 2, then we have this result that says that if there are two bounded hyperconvex domains, then they are biolomorphically equivalent if and only if um, APs are linearly isometric. Note that this is not true when p equals to 2. For we have a like a nice example. If you take look at disk, the best domain there is, and look at the puncture disk, both of them have the same Bergman space. A2 of D and A2 of the puncture disk is the same, but they are not biolomorphically equivalent. But if you vary p, then you can see that uh, they will be biolomorphically equivalent if for some p between 0 and 2, this it is linearly asymptotic. So this is one of the reasons like why you would want to study this AP spaces. Uh, so we need to develop some better tools to study these AP spaces. Uh, Now, before developing, let us look at this Berman kernel again. Uh, Earlier, we saw that you can define this Berman kernel in as a product of Rees representation theorem, or but it can be defined in other ways as well. So one is as a reproducing kernel. So it is the unique function which is holomorphic in the first variable, anti-holomorphic in the second variable, and satisfies this property. F of z equals f of zeta times the Berman kernel, uh, inner product with Berman kernel, uh, for all f in A2. The other way of defining it is as a sum of orthonormal basis. Start with some orthonormal basis, phi n, and define your kernel K in this way, sum over all these orthonormal bases. So this is one way of defining the Berman kernel. The other way is defining it as an extremal function. So what you do is uh, fix point z in your domain omega. Look at all the functions f of z which takes value 1 at that point. Consider all function f which takes 1 at which takes the value 1 at z. Now, if you minimize over the norm, then it can be shown that there exists a unique function that minimizes the norm. And that function is given by k of zeta z divided by k of z. So now you can see if you put zeta equal to z, you get 1. So this is in this family, and this function will have the least norm. So if you were to um, do it, get a analog p-Bergman kernel, you could um, try to replicate 2 or 3. I'll briefly talk about how Dr. Devraj has done some work in um, generalizing using this basis idea. And then I'll go to how to generalize using this external function. Uh, so when P is not 2, you just have a Banach space. So you cannot expect the orthonormal basis. So the next best thing you have is a shorter basis. So just let me recall what shorter basis is. Shorter basis in a Banach space A is a sequence EJ such that any x in A can be written uniquely as this sum over Cj Ej. Sorry, this should be Ej. Summation Cj Ej, and this should converge to x. Also, uh, this mapping x map to Cj of x. This should be a bounded linear functional on A. This is a shorter basis. Now, in general, it is not known if any Banach space has a shorter basis. So, but if you restrict yourself to some nice domains, then you can show that it has a shorter basis. So, in case you look at a Reinhardt domain, so that is saying that what do I mean by Reinhardt domain? If some point z1, z2, zn is in your domain omega, then the entire torus should be there. So E I theta 1 z1. So the entire circle times in all end coordinates should be there. So if your domain is a Reinhardt domain, then define this alpha in Zn to be this monomial Z1 power alpha 1, Z2 power alpha 2, so on, Zn power alpha n. Then and define this set to SP of omega to be summation. So it contains all this alphas which are in this LP of omega. So this collection will form a shorter basis for the domain AP. Now, the idea is to define a projection or kernel using this shorter basis idea. So earlier I told you that if you have a shorter basis, then the functional, let me go back. So x mapping to Cj of x, this should be a bounded linear functional on A. So the idea here will be, let me come here. So you start with an L, which is a Banach space, such that the dual of L is strictly convex. What I mean by strictly convex is that uh, um, strictly convex. If I have, say, x, y in L prime and norm x and norm of y is equal to 1, then norm of, if this is 2, then this should imply x must be equal to y. So this is strict convexity. In, yeah,
So does this mean that Banach space is strictly convex if the unit sphere doesn't contain any line segments or something like that?
unit sphere kind of. So in general, this will be less than or equal to 2, right?
Yeah, yeah.
By triangle inequality. So you want it to be strictly less than 2. If it is equal to 2, you want the function to be the same. Like it should be 2x to norm.
Okay, okay,
So that is strictly convexity.
okay, okay.
Uh, uh, and A, assume it to be a closed linear subspace of L, and EJ to be a shorter basis of this smaller domain A. And AJ are the coordinate functionals of this EJs. Now the result, so there is a result that says that if a subset of X or L is a closed linear subspace, assume that L prime or X prime is dual of X, is a strictly convex domain, then any functional will have a Han-Banach extension, right? So this will be a unique Han-Banach extension, which is non-preserving as well. So with that result, if it is strictly convex, then it will be a unique. So let us call that AJ, the unique Han-Banach extension to be AJ tilde. Now, using this, we can define a projection operator formally. Uh, now, let us not worry if this summation makes sense or not. Um, Suppose you can do, say you can do this. Now, the idea is this L is LP of omega, A is AP of omega, uh, EJ is, and omega is Reinhardt. So EJ will be those EJs that I talked about earlier, the monomials. So, and it will have a corresponding coordinate functional. And it is known that all these LP of omega is a strictly convex. So in particular, LQ, which is the dual of LP, will also be strictly convex. So we have this unique extension, and we have this as well. All right. Now, in some sense, because this is a functional on LP, you know that there is a function in LQ such that this can be written as x comma some, uh, I want to use say bj, right? Suppose everything works out nicely and you can interchange, and this is in uh, x dot bj bar, right? suppose everything works out nicely and you can interchange this integral and summation, what you get will be something like bj bar ej times x, right? So this is what we will call the p monomial basis kernel. Uh, uh, what they call actually, Dr. Debraj and Lucado. Uh, uh, okay. And the result is that, uh, so if you compute what those BJs should be and do this calculation, it turns out that this RP of ZW will turn out to be this function. And if you start with a pseudo-convex Raynaud domain, then this series, even though this is an infinite series, it will make sense and it will converge uniformly on compact subsets of omega cross omega. Also, if you have a function which has compact support, then this integral makes sense and you can define this projection operator, but it is not always guaranteed that it will extend to a AP, LP to AP. Any questions?
So for the Bergman corner, so we always wanna mention that it should be independent to the choices of orthogonal basis. Are we
Right.
expecting such a like the property here?
No, no. That is why this is called the monomial basis kernel only. Like it is
I see.
with this monomial basis only.
Got it. Thanks. Hmm.
Yeah. Any other question? Uh, so this is one way of defining using that. Out of those three that I had, one of them, if you try to generalize using the orthonormal definition, you can get it in this way. But now what I want to focus more on is the other one, which is using this third one as the extremal function. So what you do here is you can just replace this A2 with AP functions such that f of z equal to 1 there, uh, and try to get this uniqueness and existence and uniqueness, some result like that. So that is what Boyoung Chen and others did in their paper in 2021. So what you do is look at AP is F in LP, so that F is holomorphic there. Now fix some Z naught. MP of Z naught is infimum. Sorry. MP of Z naught is infimum over the norm, such that f of z naught equal to 1 and f is in AP there. So the result is that if p is bigger than 0, then there exists a minimizer function. Existence is known. But if you are looking at p bigger than or equal to 1, there is a unique minimizer as well. So we are only looking at AP for p bigger than or equal to 1. Now define that unique minimizing function to be this MP with dot comma z naught. And you're defining it, defining this KP to be MP of z naught to the power minus P and KP to be this product of this function with KP. So you're doing it this way just so that when you substitute P equal to 2, you get the original Bergman kernel. Uh, Earlier, I defined it using minimizing over the norm and fixing the value at the point. You can also see that you can fix the norm and try to maximize f of z. So this also gives you the uh, same quantity kp. Now I talk about some um, properties. All these properties are from various paper of these authors. Uh, First one is the transformation rule under biomorphism. Uh, if you have some uh, biomorphic mapping from omega 1 to omega 2, but we are restricting that it be from simply connected domains only. You will see why this is necessary. Uh, then and JF is the determinant of the complex Jacobian. Um, in that case, when P is bigger than or equal to 2, you have these results. So this K of omega 1 and K of omega 2, you can uh, relate them in this way. Now you can see that I'm writing this JF of Z raised to the power 2 over P. In general, if P is something between 1 and infinity, this 2 over P will be some rational number or irrational, like it may not be an integer. So that is why I'm having this condition that it be from a simply connected domain, so that I don't have all these branching problems. So this also comes from the fact that uh, let us see why this doesn't arise in case of p equals to 2. If p equals to 2, you see that this term is just 1, and this one will resembles the usual Bergman transformation formula, right? You can see this in this fact also. If you start with a function biolomorphism f from omega 1 to omega 2, then it induces a natural isometric isomorphism from A2. So you have this f hash from A2 of omega 2 to A2 of omega 1. And you can define it in this way. In fact, if you write the change of variables formula, you can see that f compose f multiplied with jf square, this will be f square, the over omega 2. So, but if you were to generalize this to uh, AP spaces, what happens is you'll get something like this. But this JF square will be JF square only. That is the Jacobian will be JF square. So you'll have to define something like 2 over P, then raised to the power P, right? So that is where the 2 over P comes in. So we call this AP preserving biomorphism if such a map from if you have start with the omega 1 to omega biomorphism from omega 1 to omega 2, then it should have a natural extension in this manner. That is just saying that this jf to the power 2 over p should be a well-defined holomorphic function. Um, so I can go back and change this transformation rule as if f is a AP preserving biomorphic mapping between two domains, any two bounded domains, then we have this transformation for P. Because only this 2 or P is not being well defined is the hindrance.
It seems Jocelyn has a question.
Yeah.
Yeah, I have a question. The Bergman p-Bergman kernels for the case p and p prime, where p and p prime are conjugate exponent, can
Okay.
we say something special about that?
I I don't think so. Uh, At least not in this one. I'm not sure if you can say something about in the earlier case, like the monomial basis kernel.
Okay.
That I'm not sure, but in this one, I don't think that connection is nice.
Okay, yeah. I mean, one is the dual of the other, so I thought there could be some connections to it. Okay, that's fine. All right, thank you.
Um, the Just some remarks on this AP preserving biomorphisms. So you saw that it is equivalent to saying that this JF square should have a well-defined P through. Also, the other way of saying it is, yeah. Also, you can see that if A2, if P equals 2, then every biomorphism is A2 preserving. Also, it is AP preserving if P is such that 2 or P is some natural number. Again, simply connected domains, everything is AP preserving. Also, if F is AP preserving, then inverse is also AP preserving. Then some other properties of the p-Bergman kernel. Uh, if you look at this product domain, omega 1 and omega 2 are bounded domains in CN1 and CN2. Then all these kernels are also product of each other. Now is one other nice property. So you started with defining a kernel as this extremal function, right? But it turns out that using that you can have a reproducing formula, but it is not as nice. So for any function f in AP, we have this f of z will be this kp conjugate times f, but there is also this nonlinear factor of this mp you have to worry about. So to compare this with the case of 2, you know that this is just integral a2 of zeta z times f of zeta d zeta. But here you have this other term that you have to write. So using this, you can see that MP of the minimal function at Z and minimal function at W are linearly independent. Now, one other nice thing is if you're just restricting yourself to simply connected domains, and you make an additional assumption that this minimal function or the p-Bergman kernel is zero free, then you can define this MP nicely, right? MP raised to the any power, you can do it nicely. So the so if it is zero free, then you can define this. So and it turns out that this raised to the power is itself a minimal function for some higher M AS domains. So, AS of omega. The proof is just you have a candidate and it just goes to show that it is in fact a minimal function. So uh, using this you can define you can easily get what the for a unit ball it should be. So it is just your look at the minimal function for case p equal to 2 and then take to the power 2 or p. So you can get an explicit closed form expression in case of the unit term. Now, this is one of the important properties. So let me go back to this where you define it. Uh, so the way you define it is you're fixing the value of the function at z naught to be 1 and then minimizing the norm, right? So it doesn't, you don't know how well it behaves with respect to z naught. You know that in the first variable, it is analytic because you're just looking at that collection, collection of analytic functions only. So it is holomorphic in the first variable, but you don't know how it behaves in the second variable. So that is an issue. But so that is why we have to study the regularity property of this. And it turns out you can, so it is proved that if you have any domain, bounded domain omega, then kp with the single variable z. So that is the norm function. You can differentiate it up to one once, and the derivative will be alpha holder with alpha being this exponent. It depends on me. Yeah. Uh,
In this
can you
expression, that derivative of kp of z, is it in the weak sense or?
no, no, in the strong sense, like the actual derivative.
Okay, okay,
So
okay, okay.
so actual
It's
derivative
C1. Okay,
with
okay,
respect,
it makes sense.
it
Yeah,
is C1
yeah.
and the derivative is alpha holder continuous with this alpha. That is
All
this.
right, all right. Yeah, thank you.
Any other questions? All right. So also notice that these two functions are different. This kp with one variable and with two variables are different. This is the function. This is the norm of this kind of norm of this function. Uh, so we know that you can differentiate with respect to uh, if this in this one parameter Bergman kernel, but not in the second variable. So what we are doing here is you are differentiating this kp of, for some they have chosen this notation that is with one variable. Uh, so fix some z naught and look at the minimizing function of at that z naught and differentiate with respect to the first variable. That will give you this. Am I making sense? Okay. Now let us see some metrics on this domain. So recall the standard Bergman metric is defined as this IDD bar of log of K2. It can also be written as this V2 of ZX. So it is uh, del bar. Uh, so Gij is del bar times log of K2 evaluated at Z comma Z. But you can also define it. I don't think there is an I here. Yeah, this is probably a typo. It can, an equivalent definition is this using this supremum definition. So what you do is consider all the functions in A2 such that it vanishes at Z and its norm is 1. Now maximize over uh, x acting on f evaluated at the point z. Take modulus and take the supremum. So this is an equivalent definition for the Bergman metric. So this is what they are using to define a p-Bergman metric. Uh, so the p-Bergman metric is defined in this extremal fashion. So p of z at z evaluated along vector x is kp of z raised to the power minus 1 or p, and supremum over xf evaluated at z for this in this family. I just want to do a few properties of this p-Bergman metric. One is it is AP preserving biomorphism. If you start with an AP preserving biomorphism, then the metric transforms nicely. So, and the other one is comparing with the Carathéodory metric. You can so Carathéodory metric, to recall, is this. Consider f in bounded holomorphic functions from omega. Look at f of z equal to 0 and it's infinity non 1. So, and maximize over xf at z. It turns out you can compare these two. So BP will always be bigger than or equal to this Carathéodory metric. And if you, when you approach P to infinity, it turns out to be exactly the Carathéodory metric. It is not, it is easy to see because it is intuitively clear, because when you approach P to infinity, this is AP is going to A infinity. Right? So one other. So I said earlier that this, if you look at this KP with one variable, KP of Z, then this is at most C1, right? So I cannot directly define this del bar, that is take two derivatives uh, of this log KP. So, but if you use the generalized Levy form definition, then you have this to be another metric on omega. So IDD bar of log KP will be a metric. Again, there is this comparison result. For any p bigger than 1, we have this IDD bar log KP will be bigger than the Carathéodory metric. Also, when you restrict yourself p bigger than or equal to 2, you have this will be bigger than the p-Bergman metric that we defined earlier. There is one more thing that I want to talk about. That is related. That is called the distance, the Skorzynski distance. So, if you know this, the Skorzynski distance is defined using this the usual Bergman kernel K2. So rho of ZW is 1 minus K2 of ZW, WZ raised to the power of, and so on, this complicated way. Why I am talking about this is because if you read through Dr. Cho's paper, you see that there is this other quantity that comes up, that is the diastasis function. It is defined this way, log of this K2. So this is exactly the reciprocal of this. So that is why I thought I'll talk about this. So it turns out to be 1 minus log of 1 minus rho square. Uh, I wanted to talk about this because um, I had defined, I had generalized this to a notion of KP, like a P Skorzynski distance. So the KP was defined if you just replace 2 with P, it doesn't work out because you don't know this product is may not be real. In fact, it won't be real always. So you have to define it in some other way. This closed form expression doesn't work. Uh, so let us see how to do it. What you do is you define a relation on AP except zero to be F is so basically you're projectivizing your AP space and look at the unit sphere. So the you with for this projective space EAP, you define a distance D of F comma Z G to be distance of F in SAP. So and with the distance in of G in the sphere. So that is equivalent to saying it is infimum over any function here looks like F divided by norm F. So because it has norm 1 multiplied with e to the IT1. So any function here looks like this. So basically you're taking infimum modes. Now, if you map from Z to this projective space, from omega to the projective space like this, MP of dot comma Z. So for each Z, map it to the class of the minimal function. Now, earlier we saw that they are not linear. So this map is in fact an injective map. So whenever Z is not equal to W, it won't be linear. So you can pull back this distance from here onto omega, and this will be a distance. In fact, when p equal to 2, if you compute what this is, it will turn out to be the that closed form expression that I showed earlier. This is in fact the same as this when p equal to 2. So this is what I had defined and looked at the property of this. So I just thought I'll mention this because it also came up as a Calabi as some function of Calabi distance earlier in this script. So these are some of the references. So mainly these three are the where all these properties are there. CX22, CZ22, and CX22. Yeah.
Yeah, thanks. So yeah, thanks for the wonderful introduction on the subject. I have a few questions. There are several things. For the two different like the abstraction of the two Bergman corner. So one was the monomial version from the solar basis. There's an extremer like the perspective to abstractize. So are those the same or those are just different for each?
Those are different. In fact, like even for the nice case of balls, I actually have a closed form expression of the p monomer basis kernel for the balls as well. And those are like two different things. They don't.
Okay. Not even proportional. They are just a different like the objects.
Yeah, yeah.
Mm, okay. So another like the question. Is about the curvature. So for the usual Bergman metric, so it is well known that the Holorn sectional curvature ranges from negative infinity to positive 2. Do we know such a like the range of the Holorn sectional curvature?
I am not sure.
Uh,
There is actually a section on this in his paper, but I don't think so. I don't know.
mm, so, so one last like the question I have is so from the like the Chang's conjecture perspective, say if the Bergman metric coincide with the Kähler-Einstein metric, then such a like the manifold should be biholomorphic to the unit disk and unit ball or the complex hyperbolic space. So do you know such a like a result hold even for the disk? I mean, the Bergman metric is the Kähler-Einstein metric. Do you know that's the case for the P not equal to 2?
I am not. I haven't worked in that direction.
Cool, cool. Yeah, this is something, some brand new direction in my perspective. Yeah, yeah, it is cool. So, yeah, any other questions or comments?
Mm. I think thanks for a really nice lecture. I think towards the end I couldn't listen. I had a long night, but I think the overview of the subject and in particular something that caught my eye is the transformation formula. I think Gunni can relate to when you have a biholomorphism. The like we were seeing something very similar earlier for when you have
Yeah.
biholomorphic
Uh,
in case you're
yeah.
trying.
This.
This
Yeah.
it just reminded me of something that Gunni has shared earlier, where for Bergman metric like kernel we have this for Zigo kernels, uh, like how these things work and so on.
Yeah. One more thing I might add is like, so if you're whenever you're looking at this transformation formula kind of things in case of AP, there are two things that you can do. One is restrict your function, biomorphic function, to something like this, which so that it is AP preserving, or else you will have to look at uh, something like uh, from one AP, you look at the other AP should be a weighted AP. So you can just what you can do, the second way to do this is just look at this with mod JF square kind of.
Mm,
So
mm,
this way, define it just as a composition. So everything is tagged on to here. So in that way, it works out. So there are two ways to do it to study the transformation under. Any other questions?
cool.
Yeah, if there are no further questions, then let us stop the record here. Yeah, thanks for the wonderful presentation today.